All right, now, this is going to be a review of ionization energy, atomic radius, ionic radius, and electronegativity, not necessarily in that order, and not necessarily ordered. Understood? Okay. We're going to hear terms like shielding effect, where I have the nucleus, and then I have the layers on top of layers that literally block, okay, literally block, right? Block, shield the effect of it, okay? Lead will block gamma radiation, will shield it, okay? If I use this book to shield, can't poke a hole through that, but yet if I have this, you know, that's not going to work. Maybe if I use two of them, I'll block it. No, I'm getting, okay, so you want to put this. Okay, so this is better. Shielding effect. Nuclear charge. Okay, nuclear charge. You'll hear terms like nuclear charge. We'll look at atomic radius. Think of, when you're looking at atomic radius, don't think of the quantum model of the atom. Think of the Bohr model of the atom, where it's two-dimensional and you're thinking literal rings, okay, or concentric circles, cutaway versions, cross-sections, okay, where you have circles, okay, rings within rings, okay, when you're thinking of the radius, okay. Think of when you talk about the ionization energy, it's going to be that electron that you write the 4 quantum numbers for, okay, yes. If I say to you lithium, the electron configuration for lithium is 1s2, 2s1. And if I do the filling, it's like this, right? That's the one right there. That's the 2s. That's the electron right there. That 2s electron. That's the one that I'm talking about, yes? If I do something like bromine, and it's going to be 4p5, right? This is going to be 4p5. Can you see this? Am I on the screen?
Yes.
Okay, so I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4p5, right? Yes? You see that? So I look at these, let me look at this final, okay? This is 4s2, and this is going to be 4p5. The filling goes like this, then it goes like this, this, yes? And then this, and then this, yes? And then the final electron that I put in is right here. So that's the one that I'm looking at, that one there. So when you're thinking of ionization energy, it's the last electron you put in. Okay? Those are that's a very quick preliminary review. So now let's begin. Can you see the whole thing here on the screen? Okay. So this is a view of group 1, right? The alkali metals, and then this is going to be period 3. Okay, sodium through argon. What I have written in, let's look at what I have written in. I have all the different rings. So sodium has 3 energy levels, correct? So I have 3 energy levels. I don't have the nucleus written in. I'm going to do that. We're going to do that together. I want to make a point with the nucleus, okay? This is the nuclear charge. NC is nuclear charge, AR is atomic radius, and EN is electronegativity. Clear?
Yes.
Okay? So, nuclear charge is blue, atomic radius is green, ionic radius is red, electronegativity is black. Are we okay with that? Is there anybody who's not with me? Yes? Yes? Okay, good. Now, let's start by putting in the nuclei of each of the representative elements. Okay? Yes? All right. I didn't put the symbol of the elements here, but that's going to be. Tell me what this is. What is that? What element is that?
Hydrogen.
Hydrogen. Together, just shout it out.
Lithium. Sodium.
Sodium. Good. Keep going.
Potassium.
Potassium.
Rubidium.
Rubidium.
Cesium.
Cesium.
Francium.
Francium. Okay. What's the nuclear charge of hydrogen? What's the nuclear charge of hydrogen? 1. Yeah, +1, right?
Yes.
Does it have any neutrons? No, it's just a proton. So the nucleus here is going to be pretty small, right? Just a dot. Probably less than a dot, yes? Now, as I go down, I'm going to be adding the protons, but I'm also going to add some neutrons in there. For instance, what's the mass number for lithium? You guys are open to a periodic table, I hope. You guys are sitting there like it's 8:30 in the morning on a Thursday morning. It's just another day in November. Oh, that's right, it is. Okay, I thought we were at Disneyland. Yes.
6.94.
So, but that's the average atomic mass, right?
Yes.
I asked for the mass number, which is 7. Correct? So it's 3 protons and 4 neutrons, right? So it's going to be bigger than the what? It's going to be bigger than the hydrogen, right? Well, we're not going to be able to make it proportional, but I just want to make it bigger. So that's lithium. That's going to be a little bigger. That'll be even more. That'll be even bigger. Okay, that's sodium. Bigger. Then bigger. Okay. Then bigger. Then bigger. Right? Clear? You get it? Approximately? Okay. So what's happening to the nuclear charge as I come down the column? What's happening to it? It's getting bigger, right? It's getting much bigger. Look at this. This nuclear charge, listen very carefully. This is big. Are you ready? Are you ready? Can you imagine if someone was 87 times taller than you? Can you imagine if someone was 87 times older than you? Is there anybody alive who was 87 times older than you when you were 1 year old? Of course. Not a lot of people, but yeah. Is there anybody alive now that's 87 times older than you? Of course not. It's absurd. But this is 87 times more powerful, bigger in terms of a nuclear charge than hydrogen. It's an enormous nuclear charge. So those electrons should be held so tightly, and that atomic radius should be so small because it's almost collapsing in on itself. So isn't francium very small? Isn't francium smaller than hydrogen? Antoine, you're saying yes? I'm being silly. Look, is francium smaller than hydrogen? No, it's enormous. It's enormous. Now open to page 180 and I want to put in the atomic radii of the elements in group 1, the alkali metals. Okay? The atomic radius. Okay, read it off to me. We'll start with hydrogen. It's in the upper right corner of each block. You get it? Red, you want to give me hydrogen? Why don't you read them all off for me, Red? 30.
156.
You got to say it loudly though.
156.
156.
Yeah.
Go ahead.
191.
191.
238.
238.
255.
255.
273.
273. And We don't have francium, do we? It's not on that chart. It's bigger, trust me. Okay, now, so, what's happening to the atomic radius as I go down the column? What's happening? What's happening to it? Yes?
It's increasing, but the distance between the stars.
Yeah, it's increasing, but it's increasing at almost a logarithmic rate, isn't it? You know, it starts off dramatic and then it kind of slows down, right? Doesn't it? Yes? You see that? Okay? Yeah? Okay. Why is it going to increase? Why is it going to be larger? What is varying here? What effect is variable as I go vertically down a column on the periodic table? Come on, guys, be with me here. Come on. There's more shield, so the shielding effect, right? The shielding effect is varying. It's increasing as I go down the column. It's decreasing as I go up the column. So the shielding effect, is the shielding effect constant? No. It's varying, isn't it? It's increasing. Okay, good. But look how, as the nuclear charge becomes really very, very large, the nuclear charge does indeed catch up, doesn't it? Yes? Because, look, the one reason it's a little disproportionate is there's not a lot of electrons on these rings, are there? There's only 8 here, right? There's only 8 electrons from there to there. 8 electrons here. But now there are 18 electrons here, right? Yeah? So it's going to be not as dramatic. Because I'm going to add 18 electrons on that ring, but the nuclear charge is going to change by 18, right? Yes? So in other words, you're putting a lot more electrons on an individual ring. Yes? These inner rings only have 8 electrons. These have 18 electrons. Then what happens when I get really hot? I get, right? So the nuclear charge is now increasing at a faster rate than the rings are being added. Correct? Because here, there's only 2 electrons here, right? You're adding the ring, right? But here you're, what? Here you're adding another ring. Yeah, you're adding another layer, but I'm putting a lot of electrons in there. But what I'm doing is, in other words, I'm not adding 9 rings, am I? I'm not adding 9 rings. Yeah, 18 divided by 2 is 9, right? But I'm adding an enormous amount of nuclear charge, so it's not going to be as dramatic, is it, as it gets bigger, correct? You get it? Okay. However, what about here? Notice what's the valence shell of the sodium atom? Which number? What's the valence shell of the sodium atom? 1, 2, 3, 4, 5, 6, or 7. What's the valence energy level for sodium? Anybody? They're asleep. I feel like I'm EMT going to an accident scene and everybody's just kind of like lying around. You don't know what the valence shell of sodium is? What is it?
1.
1? Okay, this is really hard, guys. Try to remember we've been doing this for a long time. Yeah, it's 3. You had to think about it? Is that right? You had to think, you had to Google it? Okay. You didn't remember that sodium is in the 3rd period? You didn't remember that? That the electron configuration of sodium, the short form is 3s2? 3s1? You didn't remember that? That it's 3? That's the valence shell? That's not good, guys. Is that good? Okay, can everybody kind of wake up a little bit? Should we do jumping jacks at our seats?
Yes.
No, not that. I don't want to wake up. Okay, so what's the valence shell of sodium? 3. Now the whole world knows that you're sleeping with your eyes open. You're a bunch of horses. Okay, I feel like I'm in a horse stable. Okay. Now, what's the valence shell of magnesium? 3. Excellent. Is that the same as sodium? Do you remember what sodium was? What's sodium? You remember? Okay, good. Excellent. Okay. What's the valence shell of aluminum? You have to look. 3. What's the valence shell of silicon? 3. What's the valence shell of nitrogen? I'm sorry, phosphorus. Sorry, phosphorus. I thought I confused you, right? What's the so much for me remembering something. What's the valence shell of sulfur?
3.
And chlorine?
3.
Argon?
3.
It's all the same valence shell, isn't it?
Yes.
So if I ask you about the shielding effect, is there an increase in shielding effect
No.
going from left to right across the third period? So is the shielding effect constant going from left to right
Yes.
across a row or period, specifically the third period? It's constant, right? Okay, good. But look at the nuclear charge. This is the nuclear charge. 11, 12, 13, 14, 15, 16, 17, 18. What would you predict would happen to the ring, to the third ring? The one in blue is the valence ring. What would you suspect would happen to that ring if you're increasing the nuclear charge? Would you expect that ring to be drawn closer to the nucleus, or would you expect that ring to be expanded away from the nucleus? What would you suspect would happen? Red? You weren't listening, were you? You were staring at me, the horse thing. I understand, it's not a problem. You were listening. Excellent, excellent, excellent. So what would you suspect would happen? It would expand away. Is that right?
Wouldn't expand away though because of the shielding effects, so then it has less.
It would expand away?
Well, no, because like it wouldn't expand away like continuously, but it would not be compressed in like a small.
This is one of the top students in the 10th grade.
Wouldn't it be compressed, but then like not as effective when it's like outer?
Well, because Francine, he said it was a very, very large element because it has.
Right, but we're in this. Yeah, but what we're talking about is just these elements here in the third period, right? Right. They all have the same valence ring, the same valence. Let's call it. Can we call it a ring? It's their shell. It's an energy level. I know, but we're going to call it a ring. Is that okay? Okay. Does it all have the same outer ring?
Yes.
Okay. If all is even, wouldn't the atomic radius be the same for all three? If all else is even? Yeah. If it's all the third ring, and all else is even, I'm not talking about shielding effect, I'm not talking about nuclear charge, I'm not talking about anything. If it's all the third ring, it would all have the same atomic radius, right? Okay, right? Right? Okay. So, shielding effect is constant, so that's not even an issue, is it? It's constant. Sodium, argon. But isn't the nuclear charge, I mean, why do the rings, why do the energy levels stay where they are at all? Why? Have you ever have you learned that, or have I taught that? What keeps an electron in the second level? What keeps any electron in the second level for sodium? What keeps any electron in the first level, such as hydrogen or uranium or anything? What keeps the electrons in orbit around the nucleus? What keeps them there? God did it? I mean, what does it? What actually does it? What keeps those electrons orbiting the nucleus? I'm asking you. That's a question. Yes?
The protons in the nucleus are drawn towards the...
Yeah, there's some kind of, do you have to write a paper on it? Are you a graduate student? No. I mean, it's a pretty easy concept. You could make it simple, right? And you could say, well, it's some kind of charge thing. Positive nucleus, negative electron. Positive, negative, and that's what keeps it around, right? What keeps the moon in orbit around the Earth? It's like a gravity thing, right? Right? I mean, there's a reason it's there, right? Right? Well, what's the reason the electrons are staying in orbit around the nucleus? Yes?
Because the nucleus and the nucleus has the protons and neutrons which are much larger than the electrons, and it has more mass
So you think it's a gravity thing?
Maybe, yeah.
Okay. But what do you think? But what do you think is more likely?
The charge.
Yeah, the charge thing. Can we say it's a charge thing? Well, we could say it's a gravity thing maybe, but it's really a charge thing, isn't it? It's a charge thing. Yeah? Yeah, it's a charge thing. It's a nuclear charge thing, and that's really what it is. Right? Yeah. I mean, a proton has a mass of like 1 × 10⁻27 kilograms, right? So if you add, if you're comparing sodium, with argon, it's a little bit more than 3 × 10⁻27. Can we just say it's 1 × 10? I'm sorry, it's more than 1 × 10⁻27. Can we just say it's 1 × 10⁻27? Yes.
It's 1.67.
All right, it's 1.67. So it's 2 × 10⁻27. Is that okay? Times 10⁻24? Oh, it's times 10⁻24 kilograms.
Actual mass of grams.
All right. Okay. Okay. So, all right. So what are you saying? It's grams? What are you saying?
Proton's actual mass of grams is 1.67 times 10 to the negative 24.
All right. So it's can we round it to 2 × 10 to the negative 24th? Is that okay? It's pretty small. Would you say it's small? I mean, it's really tiny, right? Tiny, 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 right?
Yes.
2 × 10 rounded, 2 × 10 to the negative 24th. It's tiny, right? Right? So, right? So you're comparing, though, 2 × 10 to the 24th with 16 × 10 to the 24th. You're adding only that much mass, right? So is it going to be that much of a gravity thing, Will, do you think? No. It's going to be a nuclear charge thing more than anything, isn't it? So do you understand? And how are the electrons arranged? They're arranged in rings. Remember I said the Bohr atom, do the Bohr atom thing model, right? 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 So the Bohr atom, you look it up, right? You remember? Oh, you remember the Bohr atom?
Yes.
Excellent. Very well done. So I'm asking you a question. If the shielding effect is constant, and they all have the same outer ring, which is the third one, what do you think is going to happen to that ring as I increase that which is causing the ring to stay close to the nucleus? If I increase the nuclear charge, what do you think is going to happen to the ring?
It's gonna be attracted.
It's going to be drawn into the nucleus more tightly, isn't it? It's going to almost collapse in on itself, it won't it? The volume's going to shrink. Okay? The volume's going to shrink in on itself. Yes or no?
Yes.
Okay? Yes.
What happens if it collapses on itself?
It's not going to collapse on itself, and I don't really want to speculate. I want to get through this material. Okay? It's already getting late. Okay? Yes? Okay. So, right. I'm going to stop this for a minute, and then I'm going to start it again, okay? Okay, good.